Thursday. Write that on the board. Okay. So, midterm. Midterm exam is Thursday, 8th of March, and it's 8 a.m. to 9:30 a.m. in this room. So it will be, so on everything covered so far, up to and including the real Klein-Gordon field, which we're going to finish in detail this week. So basically everything up to and including what we do today and Thursday. So that's the midterm exam, Thursday, 8th of March. It's not this Thursday, next Thursday. 8 a.m. to 9:30 a.m. Okay. So, where were we? So last time we noted that so symmetries we were talking about a general symmetry transformation of the form where U is a unitary operator that can be written as the exponential of I times a Hermitian operator. And we noted that, so this operator T is often called the generator of the symmetry. And we noted that generators of symmetries are conserved. Important general conclusion, generators of symmetries are conserved, and that is because the generator commutes with the Hamiltonian, so from the Heisenberg equation of motion, the generator is constant in time. Now, conserved quantities you will have looked at how to obtain them from Noether's theorem. So these are classical conserved quantities. So the general idea is that invariance of the Lagrangian density implies some sort of equation that looks like this, a continuity equation. And this implies that the quantity f, if I define f0, which is the integral over all space of the time part, so this f is a conserved current. Conserved current, then this is conserved. This quantity F0 is conserved. dF0 by dt is 0. So, so a good example is that if we change, let's just do the case where there's just one field. If L is, if the Lagrangian density is invariant under a change, phi goes into phi prime plus, phi goes into phi prime equals phi plus delta phi. If there's some small change in the field, if the Lagrangian density is invariant under that change in the field, then you find that this quantity is a conserved current. You take the this blackboard is full of quantum noises. So this quantity here is a conserved current. And so in particular, F0 is equal to the integral over all space. What am I doing here? So of course F0 here, dL by d phi dot, so that will just be the canonical momentum. So this quantity here is conserved. Now the classic example, which you should have done classically, we're going to write it down again and then look at the quantum, what it looks like in the quantum theory, is charge conservation. So, and in fact, it was actually a bad idea to just do this with one field, because you only get charge constant, you get charge when you have a complex field, so you need, the field and its complex conjugate. So let's say I have multiple fields here, multiple fields labeled by an index R, and here, so I should replace this by phi R alpha, and then here there's an index R that is also summed over. So there's pi R delta phi R. There we go. So let's look at the example of charge conservation, where you have the Lagrangian density is invariant under the following change, phi. So let's write it like this. We have phi goes into phi prime that's e to the I epsilon times phi, and we're going to take epsilon to be small, so 1 plus I epsilon phi, and then we treat the complex conjugate as an independent field. If you like, you can think in terms of the real and imaginary parts of two independent real fields. Doesn't really matter which way you look at it. So the new field small epsilon, I have these transformations. So what this means is that the change in the field phi is I epsilon phi, and the change in phi star is minus I epsilon phi star. Now, if you look at the Lagrangian for the complex Klein-Gordon field, which looks like this, we'll be doing the complex Klein-Gordon field in detail probably next week. But anyway, you should have probably had looked at this. But anyway, this is the Lagrangian density for the complex Klein-Gordon field. And you can see that, well, clearly it's invariant under this phase transformation. If I change phi and phi star like this, the phases cancel in each term, and the Lagrangian density is invariant. Okay, the Lagrangian density does not change under this change of fields, and this implies, the fact that the Lagrangian density does not change implies this conservation law. Implies this conservation law here. Okay, where F alpha is given by this. So for this particular case, where the changes in phi are given by this, we can plug these expressions into here and use the fact that, of course, the momentum density canonically conjugate to phi is equal to phi dot star. Okay, I take the partial derivative of this with respect to phi dot. You should get phi dot star. And so this is the canonical momentum density conjugate to phi. The canonical momentum density conjugate to phi star is dl by d phi star dot, which comes out to be phi dot. Now, you may notice that these are conjugates of each other. If I take the momentum density conjugate to phi star, and I take the momentum density conjugate to phi, they're conjugates of each other. And because of this, people tend to write just pi and pi star. In other words, you write pi to mean the momentum conjugate to phi, and you write pi star to be the momentum conjugate to phi star. Okay, so you just might be saying, oh, what's this pi and pi star? This is what you mean, but because they're conjugates of each other, you may as well just write pi and pi star. All right, so where are we? So now we can write down our expression here. Remember here we have the sum over R. The sum over R. And so what is our expression for this conserved quantity? The expression is I substituting in these expressions for delta phi, and for pi we get I epsilon times the integral over all space of well, let's see. All right, we can leave it in terms. Let's leave it in terms of pi. So pi put in the arguments. Let me put in the arguments. Okay, these are of course functions of position and time. So phi xt minus phi star xt phi star xt. All right, where pi and pi star are, you could write pi. This is pi is phi dot star, and this is phi star, which is phi dot. But anyway, we're writing in terms of phi and the phi's and the pi's. So now what we can do, so this is a conserved quantity, so you can multiply it by a constant and it's still conserved. What we do is we define the following Q. It will turn out to be convenient to write this as minus IQ. So we define a conserved quantity to be minus IQ times this same integral, where Q is going to turn out to be the charges of our particles. So let's just write this as phi pi minus pi star phi star. All right, so far that is all just classical, and you should have done that with Introject, but anyway, there you go. Quick review of what you really need to know from that is that the invariance of the Lagrangian density under this phase transformation implies a conserved quantity from Noether's theorem. This is the quantity. Now let's look at the quantum theory. Okay, now let's look at the quantum analog. So, promote phi, q, all these quantities become operators. So, all right, so what is so we're looking now at the charge operator. The charge operator for the complex Klein-Gordon field. What is it? The charge operator is just, from this classical expression, replacing the fields by operator fields. We have minus IQ times the integral over all space of phi hat xt phi hat xt minus phi hat, so the complex conjugate becomes a Hermitian conjugate. Dagger xt phi hat dagger xt. And note that the complex Klein-Gordon field it's not Hermitian. The operator field are not Hermitian. Phi and phi dagger are different. All right, so now now it's going to get interesting. Okay, now it's going to get interesting. Let's look at the commutator. We're going to look at the commutator of the charge operator with the field operator phi. So, here we have a homework problem. You should be able to show, well, so, okay, let me just write what is. We're looking at the commutator of, all right, well, let's actually just look at this. Just think about this. So we're going to take the, let's write Q. All right, let me just help you along a bit. Let's write Q. We don't want to confuse the x argument here with the x argument in this integral. So let's replace this x argument in the integral by an x prime. All right, let's write, what have we got? Minus IQ, minus IQ, integral p3 x prime. And what am I looking over there for? I've got it written up here. Okay, so our charge operator, we have minus IQ, the integral d, so let's replace the x here. Let me just write it here. Let me do what my evaluator always tells me I'm not supposed to do. There you go. Let's put x primes here. We always replace these by primes. All right? And now let's think about let me just write it out. Let me put round brackets here so you don't get confused with the commutator. t, phi hat dagger, x prime t, and we're taking the commutator with phi hat xt. All right, so this thing here, all of this here, is just the charge operator. And I want to take the commutator of that whole thing with the field operator at the point x. Now remember, the integral is just a sum. Okay, so it should be clear to you that this is equal to minus I q times the integral over all space of the following commutator, phi hat x prime t, phi hat x prime t minus phi hat dagger x prime t, phi hat dagger x prime t, commutator with phi hat xt. All right, I've just taken out this constant and the integral. So I'm taking the commutator of this expression here with the field at the point x. Now, remember, the canonical commutation relations, which for the complex Klein-Gordon field. So remember that the let me write it like this schematically. Let me just write phi fields. So we're talking about at equal times. The fields at different points commute. The canonical momentum densities at different points commute. Whereas writing it out, phi hat xt, phi hat x prime t is equal to I times the and similar for phi hat dagger, phi hat dagger. Okay, for the field phi, the canonical commutation relation with its conjugate momentum is just this standard, is I times a delta function. Similarly, phi dagger with pi hat dagger has the same commutation relation, they're conjugate fields, blah, blah, blah. So you should be able to see immediately that here, well, and also, sorry, I should also point out to you that, of course, what about the commutation relation of phi and phi dagger? Well, they're independent fields. Remember, we treat phi and phi star as independent fields. So the commutator of phi and phi dagger is 0. The commutator of phi and phi dagger is 0. So in other words, think about this. You've got these two independent fields. You've got phi with its canonical momentum. You've got phi hat dagger with its canonical momentum. These are independent fields. So the phi's commute among themselves. The pi's commute among themselves. Phi daggers commute among themselves. So do the pi daggers. These commute with each other. Okay, they're independent fields. So the only commutation relations that are non-zero are for phi with pi and phi dagger with pi dagger. All right. So if you look at this, again, it's one of those things when you've done this before and you're used to this kind of thing, it's just obvious, you write it down. Okay, phi, this term phi obviously commutes with all of this. Here we've got just pi daggers and phi daggers. So this this gives 0 contribution to the commutator. Phi also commutes with the phi here. This is just phi at a different point. So in other words, if you're a bit, with a bit of experience, you would have just looked at this and just written down, okay, so obviously the only non-zero term is I've got minus IQ times the integral over all space of, what do I have here? Pi hat x prime t commutator with phi hat x, run out of space. Run out of space. Let me write it over here. Going over to the other board. So the commutator Q hat phi hat xt is equal to minus IQ times the integral over all space of the commutator of phi hat of x prime t with phi hat xt, and here multiplying phi hat x prime t. All right, I'm just taking the commutator of this with this piece, noting that, well, phi hat at x and phi hat at x prime commute, so I just have the commutator of pi hat with phi hat, and this term, other term is multiplied here. And of course, you know, what is this equal to? This is equal to minus I times the Dirac delta function, okay, from the canonical commutation relation. And so, what does this come out to be? So that's just a delta function, minus minus cancel, I squared is minus 1, so I get minus q, and I've got the delta function, so it just picks out phi hat at the point x, xt. So that is the value of this commutator. Now, why is that interesting? Why is that interesting? Okay, here is where the interpretation in terms of charged particles comes in. That so let's just look at this. Q hat phi hat xt is equal to minus q phi hat xt. So this implies the following. So if, let's say we have an eigenstate of the charge operator. Okay, we've got some quantum state that is an eigenstate of the charge operator with eigenvalue q primed. Then you can easily show that, well, let's look at the state phi hat let's consider this new state where we take this state q prime and we act on it with the field operator. You can show that now this is also an eigenstate of the charge operator, but with eigenvalue q primed minus q. So I'll leave that to you. The homework problem is pretty straightforward. From this commutation relation, you fiddle around a bit, you should be able to show that, well, if this is true, then this is also true. So what is happening here also, and you can also show that what happens if I act on this state with phi hat dagger. So I take this eigenstate of the charge operator with eigenvalue q prime, I act on it with phi hat dagger. This is also an eigenstate of the charge operator, but with eigenvalue q prime plus q. Q prime plus q. There you go, just a simple bit of algebra, and you can show this. Now, what is going on here? So what we're going to see is that, so the physical interpretation is that when we do the quantization of the Klein, but when we look at, when we look at the expansion of the Klein, of the complex Klein-Gordon field, just write it here schematically, the Klein-Gordon field is going to be expanded in plane waves, the usual thing, but the expansion is going to take this form. We're going to be summing over plane waves, and we're going to have your A hat that you're used to, and you might be expecting, then we're going to have a, here I'm leaving off, here of course there are plane waves, I'm just schematically giving the coefficient. You might think it's going to look like this, but no, this is true when the field is real or Hermitian. Okay, you take the Hermitian conjugate of this, you get the same thing. What happens here is there's a different set of coefficients. You have A hat plus B hat dagger. And the Hermitian conjugate then looks like the following. I take the Hermitian conjugate of this, and I have terms of the form B hat plus A hat dagger. And what happens is that A, back here, so A hat dagger K, or A hat K, creates or annihilates particles of charge plus Q. What is happening here is you get two kinds of particles with positive and negative charge. Let me just write this down and then I'll explain it. B hat dagger K, B hat dagger K, or B hat K, so creates, annihilates particles of charge minus Q. So what happens? Let me just check we've got this right. So let's look, here we had a state with charge Q prime. If we act on it with phi hat, we're going to act on it either with A hat or with B dagger. A hat will annihilate a particle of charge q. In other words, it takes away a charge q. So the charge of the state diminishes by q. Or phi hat can create a charge minus q. So it adds a negative charge, and again the total charge is diminished by q. Similarly, if you look at phi dagger, what it can do is there's either B hat or A hat dagger. B hat will annihilate the particle of charge minus q. It takes away a charge of minus q. So the actual charge of the state increases by q. If instead A hat dagger acts, that creates a particle of charge plus qing. So again, so the upshot of this, and we'll see it, we do the formal, all the details with the field operator expansion, but just so that you get the idea now, is that we have, for the complex Klein-Gordon field, you find that there are two types. Two types of particle-like, let's call them particle-like field excitations. There are two types. So remember, particles are excitations of field modes. There are two types of field modes here. You have A hat K and A hat dagger K, and you also have B hat K, B hat dagger K. These are annihilation and creation operators for particles of charge plus q, whereas the B's and the B daggers, which also obey the usual commutation relations for annihilation and creation operators, these are annihilation and creation operators for particles of charge minus q. All right. So, final thing on this. Remember we said that, finish up about charge conservation. Remember we said that the so generators of symmetries are conserved. So the conserved quantity looking at this conserved quantity, the charge operator. That conserved quantity Q, it should generate the phase symmetry remember we started out at the classical level, the way we derived the expression for the conserved charge was from the following phase symmetry. Where we said, well, so you replace phi by phi prime, which is e to the I epsilon phi, which is approximately 1 plus I epsilon phi, and you replace phi star by this here. Now this should, at the quantum, this is classical. So at the quantum level, this should be described by, remember, symmetries in the quantum level are described by a unitary operator. U, which here should be e to the I, let's just write alpha, some parameter alpha, Q. All right, the phase symmetry at the quantum level should be described by a unitary operator, which is an e to the I times a constant times our charge operator. Remember the way these unitary operators generally transform any observable. Omega becomes omega primed, which is u omega u dagger. So if all of this is, if what we've done is consistent, it should be that our charge operator generates this phase symmetry. Now, what you can do, it's something straightforward, so let's check. Let's check. How will this unitary transformation change our field operator? Let's say we've got our new field operator is going to be u phi u dagger. Okay, this transformation at the quantum level will change our field operator. Just this law applied, replacing omega by phi. So what is this? This is e to the I alpha q hat, phi hat, e to the minus I alpha q hat. Now this should come out to be, this should look like this. This should give us something like the phase transformation. If it doesn't, then we've done something wrong. So let's check. You can show for small, if I look at small alpha, where e to the I alpha q is just 1 plus I alpha q, this comes out to be, for small alpha, and we looked at this similar expression last time, small alpha, if I replace e to the x by 1 plus x, and just multiply this out, some terms cancel, you find that this is just phi hat plus I alpha times the commutator of q with phi. Now the commutator of q with phi, remember we showed the commutator of q with phi is equal to minus q phi. So I can write this as phi hat, I'll take this out, I can write this as 1 minus I alpha q phi hat. Okay, substituting in the commutator is just minus q times phi hat, so I get a minus I alpha q. So if you look at this, and let us put, let us take epsilon to be equal to minus alpha q. You should see that these are actually the same. This phase transformation, 1 plus I epsilon times phi, that this is actually, if I take epsilon is minus alpha q, this is the same thing. Of course, here we're talking about classical fields of phi and phi star. here talking about operator fields, phi and phi dagger. But you can see that I recover actually, so at the classical level, we do this phase transformation, we have this conserved quantity charge. We then promote this to an operator, okay? Now conserved quantity should generate the same symmetry. It's just a general feature that we've seen. So let's look at the symmetry transformations generated by the conserved quantity. This is how it will act on the field, and lo and behold, because of this result for the commutator, it does indeed generate phase transformation at the field operator level 2, and so everything looks consistent. So, are there any questions about that?
So, when we talk about the field as an observable, as an operator, because we justify it as that it is an observable in quantum field theory. But here with the equations that the field is actually reducing the charge or increasing the charge.
So you're worried that the field is not Hermitian?
About that, not that it is not Hermitian, but that the field is not representing an observable. It is creating or
well, so if you were interested in measuring the field itself, you could think of the field in terms of its real and imaginary parts, and so you'd be dealing with real quantities that are Hermitian, and you could imagine actually measuring the field values. If you're just interested in measuring things like momentum, energy, and charge, then the observables are the momentum operator, energy operator, and charge operator. And then the field operator is just a sort of auxiliary quantity that's appearing in the formalism. That the things you're interested in would be the charge operator, momentum operator, and so on. So it just depends on what you're interested in measuring. But anyway, maybe we can talk more. Okay, so I just wanted to finish by just making sure we've got clear the other operator, the other expressions for the conserved quantities at the operator level, and then we will have finished all of the formalism, and we can then just plow ahead and develop quantum field theory. So just finally, so phase symmetry. Phase symmetry implies charge conservation. We have a charge operator Q hat. So we can also think about, all right, so you will have done this, that the, let me write this, I could write these all together, translations and rotations in space-time. So you should have done this, that I can replace my, if I think of a change, in a shift in the reference frame in space-time, my coordinates x alpha are replaced by x alpha prime, which I can write as x alpha plus, let's just write it directly, x alpha plus we're going to take these to be, these are small, so we're talking about small or infinitesimal. So these could be, these quantities here describe translations in space and time. these quantities here define rotations in space-time. Now, if I'm just looking at the space-like parts, I'd be talking about a rotation in space. If I'm looking at the space-time component, then it's a rotation in space-time, which is actually a Lorentz transformation. Okay, so these are Lorentz transformations, or rotations in space. So of course what I mean is, if I'm looking at x and y, and I rotate about the z-axis, then I'm just doing a rotation in space. If instead I'm talking about x and t, and I do a rotation, well really this is a Lorentz transformation, all this calculation. Anyway, so generally, in the general formalism of classical field theory, under such a transformation, the fields phi, this collection of fields, transforms into let's write it phi r prime, which is phi r plus a half epsilon alpha beta s alpha beta rs phi s. So you did do this, Indrajit? You did it? Okay. So this is just a general way of writing what the result would be for some general set of fields with components phi r. Here you're summing over r, you're summing over s, or with alpha beta is summed over, s is summed over. Don't worry about this too much. If phi, for instance, was if I had, say, 3 different fields phi, and they could be components of a vector field, then these matrices would just be such as to give you the right transformation law for a vector field under rotations. In the more complicated case of the Dirac field, we'll see later what these transformations are. But this is just some general matrix which can be written like this. And it's just a general expression for how a set of fields will change under this transformation. Now, what is of interest to us, perhaps I should have noted epsilon alpha beta is this is anti-symmetric. So this is really, if I'm talking about x and t, this is an infinitesimal Lorentz transformation. If I'm talking about x and y, it's an infinitesimal rotation around the z-axis. This sort of business. Okay. But now, what is of interest, what you need to know? What you really need to know, well, all right, so there is a general form here. What are the results of these different symmetries? Let me just note down here. So the S, this matrix, S alpha beta, S, is determined by transformation properties of fields. So the fields satisfy certain field equations. You want them to be invariant or covariant under such a transformation. In order for that to be true, you have to pick this matrix to take a particular form, depending on whether this set of fields are vector fields, spinor fields, scalar fields, or whatever. Now, the results of Noether's theorem are that if I consider just a time translation, so time translation, so what does that mean? So there's no rotation, these coefficients are 0, and I have delta I is 0, it's just the time component. I'm saying that it's just the only thing here that's not 0 is the time component. I've got a displacement in time. And if you impose the condition that the Lagrangian density is invariant under a time translation, you get a conservation law. It implies conservation of a quantity which one could write like this. It's the time component of form momentum. In other words, it's an energy, and it is equal to the integral. So this comes from Noether's theorem. It's an integral over space of pi r phi r dot minus the Lagrangian density. This is, you should have done this. Again here, don't worry too much about the derivation of this. It's a bit fiddly. You can go, if you weren't happy with the way it was presented by Indrajit, you probably were, but if you weren't, you can read it in the book. But don't worry too much. For the purposes of this course, what you really need to know is this theorem, time translation of the Lagrangian density, implies that this quantity here is conserved. And of course, what is this quantity? This is just your Hamiltonian density. So this is just the space integral of the Hamiltonian density. In other words, this is just the total Hamiltonian is conserved. It comes from time translation invariance. If instead I look at a spatial translation, if I look at a spatial translation, so there's no rotation in space-time, there's no translation in time, I just have a spatial translation, then this implies conservation. Sorry, and I'm assuming that the Lagrangian density is invariant under the spatial translation. Then this implies conservation of the spatial component of a four momentum vector, which takes the following form. We're looking at the classical level here, d phi r by dxj. All right. Now, whoops. Maybe I want to keep this. All right, let me just write it here. So, what is the, so for the real Klein-Gordon field, we can write down the results for the real Klein-Gordon field, and we can also write down, well, so these are classical expressions, but we know that the quantum expression is just going to be the same thing with the fields replaced by operators. And so the Hamiltonian operator for the real Klein-Gordon field comes out to be this here. So if you look at so this is just the Hamiltonian density. If you look at the case of the real Klein-Gordon field, pi is just phi dot. So the Hamiltonian density is phi dot squared minus the Lagrangian density. That comes out to be, we've seen this before, a half phi dot squared plus grad phi squared plus m squared phi squared. I replace this by operators, and phi dot, I can write as pi hat, if I want to write this as momentum, as in this before. The momentum operator, which I don't think we have done yet, for the real Klein-Gordon field, remember here there's a general set of fields. For the real Klein-Gordon field, there's just one field, so there's no index r here. Pi is phi dot. Here, this d by dxj, I can raise the index here and create a minus sign. And you should just check, make sure you get this right. The momentum, the vector momentum operator for the real Klein-Gordon field is equal to minus the integral over all space of phi hat dot, write this here, phi hat dot grad phi hat. So that's a new result I don't think we've looked at before. All right, this is at the quantum. These are quantum observables. This is an expression for the total energy. This is the energy operator of the real Klein-Gordon field. And this is the quantum momentum operator, the total momentum for the real Klein-Gordon field. Of course, I could have written the phi hat dot because I wrote it in terms of pi hat for h. Maybe I should write it in terms of pi hat for, let's write pi hat here. So, of course, pi hat is just the same as phi hat dot. Okay, because pi momentum, canonical momentum density for the real Klein-Gordon field is just phi dot. So here's your expression. So notice something here, mustn't get confused. You might think, hang on, the canonical momentum, the momentum density is just pi. So surely, if this is the momentum density, then the total momentum is just, you get it by integrating this over all space. So what's this doing here? What's the minus? Why isn't it just an integral over all space of pi? Okay, if this is a momentum density, I integrate momentum density over all space, I get the total momentum. So what is this nonsense? Okay, the answer is that the canonical, there's a difference between canonical momentum and physical momentum. Okay, the canonical momentum is a sort of abstract momentum that appears in Lagrangian and Hamiltonian theories, canonically conjugate to whatever quantity you're looking at. Sometimes, for some simple systems, like for instance, a single particle moving in a potential, the canonical momentum is just mx dot, which is the usual physical momentum. But in other cases, the canonical momentum is not the same as a physical momentum. Here in field theory, what you normally think of as the physical free momentum of the total field is actually given by this expression. Pi is the canonical momentum conjugate to the field element of the point. But the physical momentum is usually understood for the total field system is given by this expression. Okay, so make sure you distinguish between this is the momentum of the total momentum of the field, and so actually, if you're asking, well, what is the actual physical momentum density? It is really, this quantity minus pi hat grad phi dot. This is a canonical momentum density. It's a different kind of thing. Okay, one last thing to note is what about, we've looked at time translation, spatial translation, what about rotations? What if I have, let us see, let us just look at a rotation. Rotations. So let's take delta alpha is 0 and epsilon alpha beta non-zero. What kind of conservation law do I get? So, what does one find from this theorem? So this is something that you haven't gone over. one finds is, so rotational invariance. So we take that the Lagrangian density is invariant under rotation in space-time. So there's no translation. We're just looking at a rotation. So what happens, what you find is, and if you're interested, you can read through the derivation in the book, but what you find is conservation of angular momentum. Angular momentum. And the angular momentum is a sum of an orbital part plus a spin part. Now what we're going to be interested in, what we're going to need, is the expression for the spin part. When we come to do the Dirac field, we'll find that the Dirac field has an intrinsic angular momentum. And the expression for it that comes from this kind of reasoning, again, this is Noether's theorem. This is what it looks like. It involves this funny matrix here. Here is the, so an expression for the, let me just write you down, the expression for the spin or the intrinsic angular momentum. So it's an operator, it's a vector with 3 components that can be written in terms of a tensor like this. Define a tensor with indices ij, where ij are 1, 2, or 3. And the components, the 2, 3 component gives you the x component of the spin vector. And then there's a y and the z component. So have I written that correctly? 2, 3, 3, 1, and 1, 2. Okay. What is this tensor? Whose off-diagonal components give you so by the way, this is anti-symmetric, so the diagonal components vanish. Anyway, let me write it down. It looks like this. It's an integral over all space of pi r. Remember, I'm doing this generally for some collection of fields. This is the expression. So I have my an integral over all space of the canonical momentum density of the arc field. Then I have this matrix Sij Rs times the field phi with component S. And of course here you're summing over R and S. Sum over R and S. Now at this point, don't worry about this too much. What you need to know is that, look, under general rotations in space-time, Noether's theorem implies a conservation of angular momentum. This has an orbital and a spin part. The spin part looks like this. If I'm considering rotations in space-time for a general set of fields, and I can write the transformation law like this, where for a vector field, these matrix components will have a certain form. For the Dirac field, they're going to have a different form. If I want to know what is the intrinsic spin angular momentum for that field, it takes this form, where of course to work it out you need to know what these actual numbers are. So the only time we're going to use this is later in the course. We're going to look at the case of the Dirac field. And I'm going to show you how the Dirac field transforms under a Lorentz transformation or rotation in space-time. So we're going to figure out, I'm going to give you an expression for what these quantities actually look like. So then we'll be able to work out what this intrinsic spin angular momentum looks like. And of course, all of this at the operator level, at the quantum level, these will become operators. We will have a spin operator. And as I've said, the only time we're going to use this is for the Dirac field. So we're going to have operator fields including the various components of the Dirac field, and we'll have an expression for the intrinsic spin of the Dirac field. That's what we will use. And this is where it comes from. And if you want to see exactly the derivation of this expression, you can go through it in the book. Okay, so we have now done all the formalism. So from Thursday, this course is going to accelerate. We're in the car, we're going to push the accelerator pedal. Because you now know everything. You know everything about, you know what quantum field theory is, you know how the formalism works, you know how to quantize a field. So we're just going to whiz through now the next few lectures. We're going to whiz through the real complex Klein-Gordon fields, and we'll do the Dirac field, and then we'll go on to discuss interactions between these fields and the various processes, particles being created, destroyed, things that can happen. So please make sure you understand all of this, because we're just going to whiz ahead now, assume that you know all this, we can just apply this formalism, and so on Thursday we'll get going. And if there are any questions, if you have any issues, please email me for an office hour. Are there any questions about this? You can ask me afterwards. You already had a question. Anyone else have a question? All right, so please, if you anything you don't understand, email me, office hour, I'm available anytime.